We now move to section 11.2, where we learn about a position controller. In this section, we're going to understand how we might think of the position controller in terms of a mass spring system, along with the natural frequency of such a system, and how that affects the way we tune PID parameters and controller bandwidth. We will also look at the dynamic response of the system. If we open our position control launch file here in example controllers, which we did before, we see at the bottom that really we're launching two controllers, one to return the joint states and the other one to reduce the error in the desired position and the set point. Remember that for the controller parameter file in the config folder, we must reference the robot name, one.robot, before we do anything else. So we see that right here at the top of our config file, and that's the name of our robot model. And then for each joint that we have in a robot, the control gains must be listed. Here we only have one joint, but if we had multiple joints, we would just repeat the information. You can click on this file for the Baxter robot to be able to see an example of how this looks when you have multiple joints. So in this case, for example, we have 7 joints right here. For our one joint case, it's a very simple design. What we're saying here is we're going to have a PID controller with a p-value or a p-gain of 400 newtons per meter, and currently we're going to set the other gains to 0. So one of the questions will be whether or not this value is appropriate for our controller, and we'll learn how to vary that with RQT reconfigure and come up with a value that might make more sense. There's an interesting note here that we have our derivative term d set to 0, but in the Sacro file we have a damping value. And the thinking here is that actually for the simulation in Gazebo, damping has better overall effects than just playing with this number right here. It's even better behaved than if we used a velocity forward feedback term and the controller. So I'll explain this later in the video again, but instead of computing the error and the velocity, sometimes we can just feed forward the velocity term and multiply it by the derivative gain, this one right here, to have a better response in our system. But in our simulation, we find out that providing a damping gain or damping value for the system will usually have better performance than varying this number. And tuning will be done through RQT reconfigure. You can come over here to the ROS control tutorial and just see the tuning the PID gain section for a little bit more detail. Remember that RQT reconfigure is a capacity for a node that you have to create by yourself. Now, having set that for ROS control, the node already has RQT reconfigure code set up, so you don't have to do it. But in general, this is something you would have to do by yourself. For the Gazebo simulator, the controller or the cycle there is running at 1 kilohertz. You can also think of this as sensor feedback. You're going to get sensor information about the joint states at this same rate. Now, when we need to think about our controllers, our PID gains are going to actually affect the bandwidth or the frequency of the controller. In fact, you want the controller bandwidth or the controller frequency to be 10 to 20 times smaller than that of this sensor feedback loop. The concept comes from the Nyquist principle. And Nyquist principle is based on how many samples do you need to have in order to reproduce a signal. And that number normally is, depends how you see it, 2 or 1/2 of the samples. For the controller, it's similar but a little bit different. If we only have the same number of sensor readings as we do in the controller, there's going to be a lot of error that's going to come from there. The more sensor readings that we have, the better information we'll have about the data coming in, and this will reduce the amount of error that comes from sensor measurements. Now, we talked about controller bandwidth before. The question now is, how do we compute controller bandwidth? Actually, the first thing we need to do is get the way we do that is by getting the natural frequency from a mass spring system. We don't talk yet about a mass spring damper system, but just about the mass spring system with an undamped natural frequency. Down here, I have a few links for you that introduce the mass spring system and how we have this differential equation that we're trying to solve, and once we have initial conditions and solve for x dot dot, we end up having this k divided by m term that can be associated with this natural frequency, or otherwise known as the square root of k over m. Now this k is the same k that we need to assign for our gain derivative, so our proportional gain, so this kp. So take a look at the video. This information over here also helps us to get more insights from a subsequent video in the series. And then we also have the information about damping and damped oscillations over here. So if we take this equation for the natural frequency, the square root of kp over m, and we know that the value for p is 400, the mass for the second link is 1 kilogram, that's the link that the joint has to carry, then we're going to get this frequency of 20 radians per second. Now, this can also translate into a frequency of 3 cycles per second because we're looking at the number of revolutions that takes place for every 2 pi. So 2 pi is about 6 something. 20 divided by 6 is this 3 cycles per second, or 3 hertz. So what this is saying is, for a value of p equal to 400, the controller has a frequency of about 3. Basically, up here we say that we want to have a controller with a bandwidth 10 to 20 times smaller than that. So if this is 1 kilohertz, we're talking about 50 to 100 hertz. Right now we have 3 hertz, so we'll see how that is going to be useful for us later on. We're going to get things started in a second. Here, one important topic for us to look at will be the namespace one.robot and then joint one position controller command. In this topic, we will be able to publish a particular number and then drive the motor to that position. And once we do that, we'll see how in our RQT plot we have the commanded value over here. So for example, we might start at 0 and then switch to negative 0.5 and see how the effort changes in this sine curve, and also see how we get a dynamic response of the system in terms of the actual position of the encoder. We'll also then switch not just to a step command, but a sinusoidal command. And the first thing we want to try is assign a frequency of 20 radians per second, because that's what we found out to be for the natural frequency of the system. And so we want to see when we have an input of 20 radians per second, what kind of tracking performance do we get from the controller. One thing we want to do is just keep the amplitude small in a range of 0.1. We're going to offset the value to negative 0.5 as this is the middle range of the joint. So basically in terms of amplitude, we're going to go from negative 0.5 to negative 0.4 to negative 0.6. Now, given that our topic has a publishing rate of 100, by dividing that number by 5, we're going to have this frequency go up to 20 as this variable I goes from 0 to 100. And so we're doing this sinusoidal curve with 20 radian per second frequency. Yep, and so we'll get a curve that looks like this. And when we see that our reference in blue is here and our actual position in red is here, they're not matching, we know that the system is lagging and that we're not getting good tracking performance. Yep, here we can see that amplitude. We go from negative 0.5 to negative 0.4 down to negative 0.6. That's our oscillation. We have the sine frequency at 20 radians, same as the undamped natural frequency, and the result is some poor tracking at 3 Hertz. We also see a lag phase of 90 degrees. From here to here we have 180, so this is about half of that. And what we're going to see in a second is we're going to play with the gains, change the value of the gains to see what gives us better performance. Okay, now let's get this started. And of course, all of this analysis for the system response is going to be done through RQT-Plot. And we're going to use a new RQT program called the RQT GUI. And this is going to let us to actually launch so many different kind of ROS tools. We're going to do a ROS topic publication here to create the sinusoidal wave and then use the RQT reconfigure, to do the tuning of the gains. So the way we're going to get this started is ROS launch Gazebo ROS empty world, then ROS launch example controllers, prismatic 1 degree of freedom robot with joint position control, then RQT-Plot with our 3 topics, and then RQT GUI. So we're gonna come here to the RQT GUI window, and here under expression we can set the value. This is just a publisher, so we can also go to the command window and say ROS topic pub rate topic name data equals whatever it is. Okay, this is just another way to do it. So negative 0.5. As soon as I press enter and I click on here, you see that moved and you see this response. Yeah. So now I'm going to pause that, maximize this window, and look at that response. So we can zoom in. Now because this, here you see like the red line is straight, right? Actually it's not. It's changed. But because the blue response is so large compared to the red response, it looks very small. So what we need to do is zoom in. Yeah, so you click in the zoom in. You still can't see a big difference here, but we can zoom in some more. You can see still the scale. This is going up to 20, right? So we come here and then you can zoom in a little bit more. And then you can see that what we commanded is the dark blue line. Yeah, it was at 0 before. Now it's at negative 0.5. So the change from 0 to negative 0.5 happens here. But look at the red line. Yeah, it's not changing immediately, and that's the system response. We can further zoom in, and then you get this curve. See that? And so basically the position controller tries to get to negative 0.5. It takes it about 0.25 seconds to reach this value, but then it overshoots. This is called overshooting. then it oscillates back, overshoots second time, 3 times, and about here, it begins to get close to that signal. Now this is just using the P controller, no I, no D, so this takes almost a second to become steady, still with some error, right? So this means it's a very slow controller. From our analysis before, we have a undamped natural frequency of 3 hertz. Okay, this is going to be more relevant to us when we start running a sine curve of the same frequency and see how it does. Sorry. So we saw some kind of response like this, okay? Lagging. Now, the next thing we want to do is, in the RQT GUI, introduce a function. This is something we cannot do from the command shell, but with the RQT GUI we can. And in this case, we're going to use I as a step input. So this is connected to time, So this I will have the value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 as it goes to 100. So imagine we want to publish a sinusoidal curve with a frequency of 20 radians per second. Okay? So we can use an equation like this. 0.1 is the amplitude, right? So it's the amplitude of the wave going up and down. Yeah? Around 0. We use a sine, and the frequency of our topic is what? Can you remember the frequency? For the commanded data, when we publish the data, how fast do we want to publish that? 100 hertz. So if we want a frequency, a sine curve of 20 radians per second, what do we need to do? We take this I, which in 1 second will go up to 100, and divide by 5. So every second, we go up by 20 radians. Yep. And then what we're going to do is subtract the value of all of this by negative 0.5, because that's just going to move the sine to the center of motion of the robot. Negative 0.5 is the middle of the motion of the robot, maybe here. So then we're going to do a sine curve of 0.1 around that point. So we're going to go up to negative 0.4 and negative 0.6. Yeah? So we do the same thing, and we're going to get something like this. So let's give that a try. We have a robot. Let me zoom in like this. We have our plots here. Let me bring that to this side and do auto scroll again. Maybe actually let me bring it up here. And we have RQT GUI down here. So instead of having that negative 0.5, I'm going to say 0.1 times the sine of I divided by 5 minus 0.5. So I'm going to press enter, and you're going to see that joint start doing that sinusoidal curve. Yep, that's a command. And so the question again is the system response. So let's come over here. We can see the joint effort, because the joint has to go up and down. The effort goes up, the effort goes down, also with a sinusoidal curve. But they're different units, right? Here we're working with newtons, so it goes up to almost 100 newtons to make that happen. Why? Because it has to carry weight, right? It has to push the weight of the second link, 1 kilogram, up and down, up and down. Yeah. And then, so what we can do here is pause it, and then go in and zoom in. You want to get as much time as possible, so you do the whole window. Do that, and then zoom in one more time. Something like this. So you get this kind of response. The dark blue color is what we want. That's the commanded one. And the red color is the response, right? So you can see, maybe we say, I want you to go here, but the system still takes some time to do that. Okay?
Why is it a little bit bigger than the red one?
It's not tracking well, it's overshooting. So it means our controller is not very good yet. Yep, it's not very good yet. So this also has a lag of about 90 degrees. It's our phase about 90 degrees. Let's look a little bit of what we can learn from here. So we know we can see the amplitude is 0.1. We go from negative 0.5 to, this is for the command, right? To negative 0.4 and negative 0.6. That's the oscillation. The sine wave has a frequency of 20 radians. Oh, that's 6 pi, right? 20 radians for 6 pi. And here our controller, we know, has, from the equation I showed you earlier, has an undamped natural frequency of 20 radians per second. So what we want and what we have is very similar. This often translates into the controller not being able to track properly. If you want to track properly, you need to have a faster controller. Yeah? How do we have a faster controller? From the equation that we showed you earlier. Square root of Kp divided by m.
Let the Kp here.
Larger.
Larger, yeah.
Right. So right now, we have poor tracking at 3 hertz. We have lags. The red curve is lagging by about 90 degrees. So if you kind of look from here to here, this is 180 degrees, right? And so this is kind of like in the middle, right? So it's 90 degrees behind. And so we want to increase P or I to see how it works. Now, if you want more mathematical detail, see the reference. Now, let's go back then. Actually, let me see what's the easiest way to do this right now. We do this, bring it back here again, and then do the plots. Actually, we'll leave it here, and then RQT GUI down here. What I'm going to do in the plot right now is take off the effort, because that'll change our plot. This way I can just stay with this size. And now, what I want to do is add RQT reconfigure. Yeah. So let me see. I can pull this out automatically, and I can click on expand all. Here is my PID. Okay. So now I'm going to take auto scroll away. You can see the curve running, right? Mm-hmm. So you can play with that value, but I've done some of this already. So if I change that to 2500, when I press enter, you can see that red curve getting very close. Still, there's some difference, right? The D value doesn't make much of a difference. But as I increase that I value, what I do is I remove steady state error. Okay, now you got to be careful with the I value because it can saturate. That's why we have the clamp. Saturate is we have too much error and then it becomes unstable. Too much accumulation of error and it becomes unstable. But you can have something like this. Yeah, so this is a way for us to do PID tuning. Yeah. Another thing you could consider is if you go back to your original model, set this to 0, where I publish here, I could say, let me make this a slower system. Yeah, how do I make that a slower system? I make this denominator bigger. So let's say I make that equal to 20. So now the frequency of the system is 5 hertz. Yeah. And it kind of has a little bit better tracking than before. The lag is not 90 degrees anymore. Does that make sense? So you could, with the current system, you could have a slower command, or with that command, you could have a larger P. Okay.